In our next section, we'll be discussing the role of diffusion in the creation of electrochemical gradients. In this section, we'll talk about diffusion. This slide illustrates the barriers for diffusion for molecules to get across membranes. Membranes, because they are made up of a lipid bilayer, do not permit the movement of either polar molecules or large molecules across them. The only molecules that are free to cross membranes without going through any particular barrier are gases in general, such as oxygen, carbon dioxide, and nitric oxide, and nonpolar molecules like steroids. Water can pass through membranes because of a specific channel known as the aquaporin channel, and therefore water is free to diffuse across most membranes. In this section, we'll talk about membrane potentials, which are driven by diffusion of charged molecules across membranes. And before we get into the nitty-gritty of the material, let's just go through a few useful abbreviations. Na will stand for sodium, K for potassium, Cl for chloride, Ca for calcium. These are the standard abbreviations for these molecules. Capital A will stand for anions in general. E sub x will be the equilibrium or the Nernst potential for a given ion x, and V sub m will stand for the membrane voltage. As this lecture moves on, it will be very important for you to keep clear in your head the difference between E sub x and V sub m. The important thing to remember is that V sub m is a real voltage. This is a measured value that one can use an electrode to measure. E sub x for any given ion, such as E sub sodium or E sub potassium, these are calculated potentials for any particular ion, and this will become more clear as the lecture moves forward. In the next slide, we'll discuss the origin of membrane voltages. So shown on the left is a box that has two compartments. On the left compartment, we have 1 molar sodium chloride, and as you probably know, sodium chloride will dissociate spontaneously into sodium and chloride ions, such that 1 molar sodium chloride will give us 1 molar sodium and 1 molar chloride. On the right, we have 0.1 molar sodium chloride, which dissociates into 0.1 molar sodium and 0.1 molar chloride. Initially, if we were to measure the voltage across this barrier between these two compartments, the voltage here will be 0, because there's no difference in the distribution of positive charges within any given compartment. There's no force driving ions either to the left or to the right. If we were to now make this barrier between these two compartments selectively permeable to sodium, what do you think would happen? Well, sodium would travel down its concentration gradient. That is, it would go from left to right. Well, what's the result of that happening? Well, as sodium travels from left to right and it carries its positive ions from left to right, a positive charge will build up on the right and a negative charge will build up on the left. The negative charge is caused by the unbalanced chloride ions left behind as sodium traveled to the right. Well, since sodium carries a positive charge, it will be repelled by the buildup of the positive charge on the right, and that will slow down the movement of sodium. For this reason, sodium does not just continue to travel down its concentration gradient until those two concentrations equalize. Instead, it'll stop early. And it'll stop early because of this newly created charge gradient. So we've got two forces driving sodium in opposite directions. There is a concentration force or a concentration gradient driving sodium to the right, and there is an electrical gradient driving sodium back to the left. Ultimately, sodium will reach equilibrium where there are equal rates of sodium flux to the left and to the right. So one question we can ask is, what is the voltage when equilibrium is reached? And there are two ways to get at this answer. In this particular example, we can simply measure the voltage across this barrier, and that voltage would be 61 millivolts. As we'll see, we can also calculate this voltage. One important thing to remember in terms of intuitively understanding what these voltages mean is the following. This 61 millivolts represents the amount of charge that it took to offset the sodium gradient. The sodium gradient was a 10-fold gradient. If we were to increase this gradient, let's say to a 100-fold, let's say we had 10 molar on the left and 1 molar on the right, what do you think would happen to the voltage needed to offset that concentration gradient? The answer is it would increase. It would require more of a voltage, more of an electrical gradient to offset the concentration gradient. Well, these relationships between concentration and voltage are related via an equation shown in the next slide, known as the Nernst equation. The Nernst equation relates E, which is this measured voltage, to the concentrations inside and outside of a given cell. And the equation is as follows. E is negative 61. Negative 61 is simply a constant, over N, which is the charge on the ion that we're talking about, times the log of the inner concentration over the outer concentration. And one of the most important things to remind you of is that this Nernst equation is good for any given ion, one ion at a time. Any ion that has a distribution across a membrane is going to have a Nernst equation, but this Nernst equation is only good for that given ion. So let's go ahead and do this equation, or do this calculation for this particular example. So here's a Nernst equation for the first example. So E for sodium is negative 61 over N millivolts times the log of the inner over the outer concentration of sodium. Well, N in this case will equal 1. That's simply the charge on sodium. And we'll call the compartment on the right from the initial example, we'll call that the inside of the cell, and the compartment on the left the outside of the cell. If we plug those numbers in, we get negative 61 times the log of 0.1 over 1. The log of 0.1 over 1 is just negative 1. So negative 1 times negative 61 millivolts is 61 millivolts. And that's where that charge came from. Well, let's take a bit of a more real-world example. If you take a real cell and think about what are the major ions that contribute to the voltage across the cell. What are the major ionic species, period, across the cell membrane? Well, the major ionic species in the extracellular space are sodium and chloride. And they have a dominant concentration in the extracellular space. And for the ease of exposition, we won't show you the inner concentrations of sodium and chloride because they are low, but you should recognize that there is a small concentration of sodium and a small concentration of chloride inside of the cell as well. What is the major internal cation inside of cells? Well, the major cation inside of cells is potassium. How about the major anion inside of cells? Well, this is not entirely as clear. The major anion inside of cells is comprised of multiple different types of anions. You have several things that have a negative charge. You've got a lot of bicarbonate, there are proteins, there's DNA, RNA. There are a lot of things that contribute to the negative charge inside of cells. These are all negative ions that are trapped inside of cells, and we give these the generic term A-, and this comprises the total negatively charged molecule population inside of cells. Well, under normal circumstances, the only ion that has any real permeability to the cell membrane is potassium. And potassium is therefore going to flow down its concentration gradient. That is, potassium is going to flow from inside of the cell to outside. But similar to the initial example that we gave earlier, when that happens, it's going to take its positive charges and take them outside of the cell and leave behind negative charges inside of the cell. So now once again we have two different forces. We have a diffusion force driving potassium to leave the cell, but an electrical force driving potassium into the cell. So once again, we will reach equilibrium. The important point to remember is, as you look at this, this tells you precisely why most cells have a negative charge at rest. They have a negative charge because of the efflux of potassium leaving behind negative charges inside of cells. Another feature that contributes to the net negative charge inside of cells is the sodium-potassium ATPase. As we described earlier, this pump is asymmetric. It pumps out 3 sodium ions for every 2 potassium ions that it brings in. And as such, it is also electrogenic. It pumps out more positives than what it brings in. This will also contribute a small amount to the net negative charge that most cells carry. So therefore, the resting membrane potential, this is the voltage of cells when cells are at rest, and we'll talk about what rest means more precisely later on. This is referred to as V sub m. This is a measured value. Typically, it's between -70 to -90 millivolts, and it's driven by the potassium efflux with a smaller contribution of sodium, and as I mentioned previously, a small contribution from the sodium-potassium ATPase. There are 2 important definitions to remember. Depolarization refers to the situation when the voltage across the cell membrane is moving towards 0. That is, the cell is getting more positive. Hyperpolarization refers to a situation when a cell is becoming more negative, and that is, the voltage is moving from some baseline negative value to a more negative value. What about multiple ions? Typically, we have several ions that have some baseline permeability across the cell membrane. Typically, the permeability is by far dominated by potassium. That is, potassium has the highest permeability, but there may also be some finite permeability to sodium and perhaps to some other ions. The membrane potential ultimately represents the weighted mean of all of the individual Nernst potentials, and these weights are determined by their permeabilities. And since most cells' permeability is highest to potassium, V sub m, the real voltage across a membrane, is closest to the Nernst potential for potassium. Therefore, under most circumstances at rest, V sub m will be somewhere near to E sub k, or the Nernst potential for potassium. Okay, let's do some examples. Let's say you have a situation as follows. You have a cell which has a sodium concentration of 10, potassium concentration of 110, and chloride concentration of 5. These are all in milliequivalents per liter. The external concentration of sodium is 120, for potassium it's 4, and for chloride it's 105. Let's also say that the real voltage across the membrane was measured and the voltage was -70 millivolts. And one question I could ask you at this point is, given this voltage and given all of these baseline concentrations, what direction do you think sodium is going to go? What direction is potassium going to go? And what direction is chloride going to go? Because all these ions are going to move in order to reach equilibrium. Now, one might be tempted to look at the sodium gradient, for example, and say, well, it's obvious. Sodium is going to enter the cell. It's going to move down its concentration gradient. If you were to answer the question in this way, you run the risk of getting this question wrong, because it's not as simple as only looking at the concentration gradient. One also has to look at the electrical gradient. So to answer a question like this, you need to be able to convert these concentration gradients into an electrical gradient, or into a potential that tells you what the electrical gradients are. The way that we relate concentration gradients to electrical gradients is via the Nernst equation. So shown now are the Nernst potentials for all of these various ions. And we'll just go through these step by step. So the Nernst potential for sodium is -61 over N. N was taken out because it's just +1. times the log of 10 over 120, and that Nernst potential is positive 65. For potassium, the Nernst potential is negative 61 times the log of 110 over 4, and that equals negative 88. For chloride, you have to be careful because of the charge. The charge is now negative 1. So we have negative 61 over n being negative 1 means we just have positive 61 times the log of 5 over 105, and that equals negative 81. Now we're prepared to answer this question. So to restate the question, we have a voltage of negative 70, we have a Nernst potential for sodium of positive 65, and if I said all of a sudden we're going to open up some channels and allow sodium to flow in whatever direction it wants, what direction will sodium flow? Well, whenever you're faced with a question like this, the important relationship is what's the difference between the equilibrium potential for your given ion, in this case sodium, and the real voltage across that membrane. In this case, the equilibrium potential for sodium is much, much more positive than the real voltage of that cell. Therefore, sodium is going to move in a direction to try to drive this cell towards sodium's equilibrium potential. In order to do that, sodium will enter the cell. That is, sodium enters the cell, and by doing so makes that cell more positive. It'll drive that voltage from negative 70 to negative 65 and so on until ultimately that voltage reaches positive 65. So under these conditions, sodium will enter the cell. How about potassium? Potassium has an equilibrium potential of negative 88. The real voltage is negative 70. Therefore, potassium's equilibrium potential is more negative than the real voltage. The only way to drive the real voltage to the equilibrium potential for potassium is for potassium to leave the cell, and that will make the cell more negative. We can do the same exercise for chloride. Chloride's equilibrium potential is negative 81. The real voltage is negative 70. The only way for chloride to make this cell move from negative 70 to negative 81 is by entering the cell. By going into the cell, it'll take its negative charges and make that cell more negative. So in this case, we actually found that all of the ions moved down their concentration gradients because they happen to match their electrical gradients. That won't be the case for all examples, and we'll see some examples right now. Let's say the voltage is now positive 65. What's going to happen to sodium when the real voltage is positive 65? Well, since the real voltage is positive 65 and the equilibrium voltage for sodium is also positive 65, this means that this cell, or excuse me, that sodium is now at equilibrium. The voltage matches equilibrium voltage for sodium, therefore there will be no net movement of sodium. Potassium has an equilibrium potential of negative 88. The real voltage is positive 65. Therefore, potassium's equilibrium potential is far more negative than the real voltage. The only way for potassium to drive this voltage to be more negative is by leaving the cell, and therefore it will do that to drive this voltage from positive 65 eventually down to negative 88. Similarly, chloride has an equilibrium potential that is far more negative than the actual potential. In order to drive the actual potential down to negative 81, chloride will enter the cell to try to drive this voltage to become more negative. Finally, when the voltage equals negative 90, we can go through the same process, but we'll find some interesting differences. Sodium, again, has an equilibrium voltage of positive 65. The real voltage is far more negative than that. The only way for sodium to try to drive this negative 70 up to positive 65 is by entering the cell. Potassium, however, has a different situation. Its equilibrium voltage is negative 88, but the real voltage is negative 90. the voltage is now more negative than the equilibrium voltage for potassium. Therefore, the only way for potassium to get this voltage to be not quite so negative is by entering the cell. And if you notice, in this case, that would imply that potassium would move up its concentration gradient from 4 to 110. But it needs to do that to try to drive this negative 90 to be something closer to negative 88. Similar situation exists for chloride. Now the voltage is more negative than the equilibrium voltage for chloride. The only way that chloride can make this cell more positive is by leaving the cell and therefore going up its concentration gradient from 5 to 105. So you see here it's important not just to look at the distribution of ions across your membrane and to use that to determine the direction of ionic flow. One also has to look at the relationship between the Nernst potential and the voltage across that membrane. One can now use this knowledge to understand why certain other manipulations of ionic potentials work. So potassium chloride. So potassium chloride is used during lethal injection, and the reason that it works for this indication is because it depolarizes cardiac myocytes. Well, why should that be the case? Well, we can go right back to our Nernst equation. So shown here in the middle is the equation for the Nernst potential for potassium. So E is negative 61 over N times the log of the inner concentration of potassium over the outer concentration of potassium. Under normal circumstances, the inner concentration for potassium is much, much greater than the outer concentration of potassium. And let's just put in some hypothetical numbers and see what we get. So the E sub K, the Nernst potential for potassium, is negative 61 times the log of 150 over 10, and this would equal negative 72 millivolts. And as I described to you earlier, because the baseline permeability for potassium for most cells exceeds any of the other permeabilities, the voltage across the cell will be very close to the Nernst potential for potassium. Since the Nernst potential for potassium is negative 72, V sub m across most cardiac myocytes will also be near to negative 72 millivolts. If you then provide a large bolus of potassium chloride, how would that affect the Nernst potential? Well, we can simply plug those numbers in. So our Nernst potential is now negative 61 times the log, and let's just say for the sake of argument that we've increased the extracellular potassium concentration from 10 to 150. So now we have the log of 150 over 150, and that will equal 0. So since the Nernst potential for potassium is now 0, therefore V sub m is also near to 0. And when it comes to cardiac myocytes, if one were to depolarize cardiac myocytes to the point where they all have a voltage of 0, these cells will no longer fire action potentials and therefore will no longer contract, and ultimately this will be the mechanism of death of the condemned subjects here. Question. Let's go back to your renal patient with hyperkalemia. Let's say before his renal failure, the extracellular concentration was 4 milliequivalents per liter, and the intracellular concentration was 140 milliequivalents per liter. Now that his external concentration of potassium is 6.5, what has happened to the resting membrane potential, V sub m, of his cardiac myocytes? A, they will depolarize, that is V sub m approaches 0. B, they will hyperpolarize, that is V sub m moves away from 0. C, there will be no change in V sub m. Or D, it is impossible to tell. Well, as was illustrated in the previous slide, whenever the extracellular concentration of potassium is increased, this will decrease the gradient for potassium across a cell membrane. When that gradient is decreased, the voltage for potassium, the equilibrium potential, will approach 0. When that happens, if you begin at negative and you approach 0, that means that cells will depolarize. And that's answer A. Cells will depolarize because you are decreasing the potassium gradient across those membranes. That concludes our discussion on the role of diffusion in the creation of electrochemical gradients.